Hey there, I'm Matt Gomez, and this is Field of Ferns. We wanted to compare our native fern, the western sword fern, Polycycum munitum, to a leatherleaf fern, which is an invasive fern from South Africa and South America. So our western sword fern here is adapted to be like in the understory region, not a lot of direct light, pretty humid here in the redwood forest. It can grow a little bit taller than its counterpart, the leatherleaf fern. So here's actually a really good example of how these ferns compete for light, the limited light they have under these redwoods. You see a lot of small brush, smaller bushes, and these ferns can actually grow about 3 to 6 feet tall to get that little bit of light that they need in the understory. You can also look at the leaves here. They kind of don't feel as waxy as the other fern that we are going to compare it to, which is the leatherleaf.
So like many ferns, the leatherleaf fern is also adapted to partial shade and partial sun conditions. It grows up to 3 feet high in many cases, and it's, yeah.
Like super lightheaded. Coffee and a cookie. Yeah, that's what I. It forever to figure it out.
So I was in charge of doing the cross sections for both ferns. Actually, as we see here, we actually have one of the ferns. This is the leatherleaf fern, and as we see, it has a kind of a heart-shaped vascular bundle. But for the most part, this vascular bundle is a lot bigger in the xylem conduits than the native sword fern, which we have here. The native sword fern also has a Casparian strip lining the vascular bundles, which may help it allow it to retain more water depending on the environment. Its vascular bundles, as in the xylem conduits, are dramatically smaller than the leatherleaf fern. So after these cross sections were done and examined, we went over and actually did the countings of the tick marks in the xylem width. We tried to use ImageJ, but ImageJ was kind of faulty with my computer, so we did it the old school way. So when measuring the xylem width, we actually got 3 measurements for 2 of the separate species. We got, for the leatherleaf fern, we got 45.4 microns for our first measurement. Our second one was 40.9 and 38.39 for our third one. As for the western sword fern, the xylem diameter greatly decreased, or was significantly different. The first measurement was 7.2, and then it went up to 10.6. and 7.5. You measure both the short side and the long side, and you plug into the equation, and it gives you these measurements.
So right now we're actually analyzing all the data we took for xylem width, cuticle thickness, water potential, and stomatal density. Yeah, all these error bars on on these graphs represent one standard deviation. We want to use a t-test, and after using the t-test, we look at our p-value, and anything lower than 0.05 is considered significant. So when analyzing our values for water potential, we got a p-value of 0.0019, so that is significant. That means our data means something. When we look at the graphs for stomatal density, it might have looked like our leatherleaf fern had a higher stomatal density than our sword fern, but when we actually analyzed it using the t-test, we got a p-value of 0.2302, meaning that these two plants don't really have that different stomatal densities.
Yeah.
So these are our graphs for the xylem widths of our 2 plant species, leatherleaf and sword fern. This actually kind of went against what we predicted, because we actually expected the leatherleaf fern to have thinner xylem because it was going to be more stressed for water, given that it usually kind of grows in more direct sunlight and hotter temperatures. But we actually ended up with the leatherleaf fern having significantly wider xylem conduits.
So after the stem cross sections, we moved on to the leaf cross sections, and we had some hypotheses about what we might find. For the leatherleaf fern, we expected it to have a thick cuticle, which it actually did end up having. As for the sword fern, the results kind of varied, but for the most part, it had a thinner cuticle than the leatherleaf fern.
So this actually made a lot of sense given the two native environments of these two ferns. The thick cuticle would help the leatherleaf fern prevent from wilting when it opens its stomata. It would help keep the water inside. Whereas the sword fern that's located here in kind of a more humid, a shadier area would require a thinner cuticle because it wouldn't have to worry about water loss when it's taking up CO2.
So we also found a Casparian strip in the stem of the sword fern. It's kind of unknown at this point why it's there in the scientific community. People hypothesize that it's due to it taking water from the leaves and wanting to filter it out from any contaminants or pollutants before inserting it into its xylem.
So this is our graph for our last and final factor that we analyzed. It was water potential. This is our leatherleaf fern right here, the taller bar, and this is our sword fern. And this also kind of went along with what we predicted. Because the leatherleaf fern kind of grows in a hotter environment with more direct sunlight, it would have a more negative water potential because it would need to suck in that water. So yeah, the sword fern wouldn't need as a negative or strong of a water potential because it's already in a more humid place where it's less stress for water. This grows in a hotter environment with more direct sunlight. It would have a more negative water potential because it would need to suck in that water extra hard compared to the
through the Casparian strip and before injecting itself with any pollutants or contaminants.
Hello.